Hello students, let us start our today's session from the chapter Alcohol, Phenol and Ethers. Today we are going to discuss about the acidity of alcohols and phenols. In addition to that, let's see some more concepts of the dihydric and trihydric alcohols. The different tests for identifying the given alcohols and phenols with uses. Okay, we will start our today's session, acidity of alcohols and phenols. Already we discussed about the reaction of alcohols and phenols with metals. We said alcohol that react with metal and displaces hydrogen. Phenol that to react with metal to release hydrogen and the sodium phenoxide. But in addition to the reactions of alcohol and phenol with the metals, phenol react with the even bases, the strong bases like sodium hydroxide, potassium hydroxide to form sodium phenoxide and water. So this makes the reactivity of these alcohol and phenol with the sodium metal and sodium hydroxide that makes the difference of acidity of alcohol with phenol. So how do the hydrogen is being released? Where the hydrogen behaves as acidic hydrogen, there only the metal or the bases can displace hydrogen. As alcohol and phenol, both of them losing their hydrogen upon reaction with the sodium metal, that confirms both of the hydrogen of OH group being acidic in nature. In addition to that, the phenol that may also react with the sodium hydroxide, but alcohols do not react with the sodium hydroxide. So let us see why the difference in acidity of alcohol and phenol is observed. According to Lowry-Bronsted concept, proton donor or acid, proton acceptor or base. Let us take an example, a base that is designated as B minus having a pair of electron. And with the alcohol, here alcohol that carries the OH group, oxygen is more electronegative and hence that oxygen withdraws the electron from OH bond and hence the hydrogen becomes the proton, where this proton is abstracted by the base. So as a result of accepting the proton from the acid, the BH becomes conjugate acid of base B. And here the acid, that alcohol that donates the proton, here it becomes the conjugate base of an acid. In the reverse, the BH becomes proton donor and the alkoxide group becomes proton acceptor. In the reverse of the reaction, the conjugate acid becomes the proton donor and the conjugate base becomes the proton acceptor. So we will get the reverse. So based on this, we may say proton donors are acids and proton acceptors are bases. Let us discuss about how the presence of alkyl group that may influence the OH bond. An acid is a substance that depends upon the tendency to lose the proton, and the base is a substance based on the tendency to accept the proton. The one which is ready to lose the acid proton, that is said to be a stronger acid. The one which is ready to accept the proton, that is said to be a strong base. So here the presence of alkyl group, we know those are plus I groups. Plus I groups have a tendency of releasing the electron towards the most electronegative atom. So we have taken the primary alcohol as it has one alkyl group that releases the proton towards this oxygen atom and hence increases the electron density of oxygen of OH bond. When electron density of oxygen increases, the OH bond goes stronger. So the hydrogen that cannot be released easily. So here we have a primary alcohol, only one alkyl group is to be there. But in secondary alcohol, both the alkyl group that releases the electron towards the oxygen atom of OH group. Therefore, the oxygen atom electron density still increases. In tertiary alcohol also, all the three alkyl group that releases its electron towards the oxygen atom. Therefore, electron density of oxygen atom of tertiary alcohol is much higher than those of secondary or primary. When electron density increases, the polarity of the bond decreases. So polarity, what do you mean by polarity? This is what? It accepts the proton, so that case that creates a positive charge and the negative charge on oxygen. That means the polarity. So in this case, the effect of alkyl group increases, that increases the electron density of oxygen atom and hence decreases the polarity of OH bond. So the increase of alkyl group that will not ready to lose the proton from the OH bond and hence those are weak acid. So depends on the number of alkyl groups to alcohol. The alkyl primary alcohols are much stronger acid than secondary alcohol, which is then tertiary alcohol. And that strength of the alcohol, the strength of the acidic character of alcohol depends on the number of carbon atoms in the alkyl group. The presence of increase in number of alkyl group increases the electron density of oxygen atom of OH group and hence decreases the polarity of OH bond. So there the acid goes weaker, and the size of alkyl group that also determines the acidity of alcohol, though they are primary, secondary or tertiary. So when length of alkyl group increases, that decreases the acidic character. So we may say methanol is more acidic than ethanol. Ethanol is more acidic than propanol because 1, 2, 3 number of carbon atom increases. Let us compare acidity of alcohol with the water. So alcohol, the alkoxide ion with the water it has H2O where oxygen has 2 lone pair electron and alkoxide ion. In this case, the water is ready to donate the proton to alkoxide, so we can make such a way. So we are getting ROH with OH minus. So here water is ready to donate the proton to the alkoxide. That's why water is said to be stronger acid than alcohol. Alcohol becomes weaker acid. Now let us discuss about acidity of phenol. Phenol, it has the OH group where the oxygen atom is attached to sp2 hybridized carbon atom. But in alcohol, the oxygen atom is attached to sp3 hybridized carbon atom. And we know the S character of sp2 hybrid orbital is greater and more electronegative, so that may tend to withdraw the electrons of oxygen towards the benzene ring. As oxygen has 2 lone pairs of electron, that electrons gets delocalized with the benzene ring, where the negative charges are delocalized at 2, 4, 6 position. So the formation of alcohol, that is the phenol itself stabilized through resonance due to the conjugation. The lone pair electron is in conjugation with the benzene ring. But such resonance stabilization is not observed in alcohol because alkyl group has no sp pi bond or even the lone pair electron, since alkyl group is sp3 hybridized. Now alcohol that may able to form alkoxide ion and H plus ion. Similarly, phenol can also lose the proton to form phenoxide ion. Phenol stabilized by resonance, alcohol do not stabilize through resonance because of sp3 carbon. Once again, let us compare the delocalization of pi electron or the negative charge with a compound with the formation of alkoxide with phenoxide. Once again, oxygen attached to sp3 hybrid orbital of alkyl group, and where in phenoxide oxygen is attached to sp2 hybridized carbon. Therefore, phenoxide ion is also stabilized through resonance, but alkoxide ion unable to stabilize by resonance. This is also one of the reason why alcohols are weaker acid and do not react with bases. So in phenol, we are after the loss of proton, we are getting the phenoxide ion. So here that electron negative charge, it gets delocalized over the benzene ring. So once again phenoxide ion is also stabilized through resonance. So from this resonance stabilization, it confirms phenols are more acidic than alcohol. So phenoxide ion is further stabilized by resonance, but such resonance stabilization is not observed in alkoxide ion because of the oxygen attached to sp3 hybridized carbon. Now let us discuss about the effect of electron donating group and electron withdrawing group on acidity of phenol. These electron donating and withdrawing group with respect to the position of ortho, para, meta, they influence their acidic character more. So depends on the position of electron donating and electron withdrawing group, the acidic character of the substituted phenols can be altered. Suppose if the electron donating and withdrawing group are at para position, those are said to be, compared to their isomer, stronger. See, we have taken CH3OH, that is para hydroxy toluene, or we can say it is para-cresol. This is para-cresol. And here it is a phenol, and the other one is it is para-nitrophenol. So the phenol, it has no any other substituent, and the acidic character of phenol is compared with the substituted phenol. In cresol, the para position is occupied by CH3 group, and in nitrophenol, the para position is occupied by NO2 group. The CH3 is electron donating group. CH3 electron donating group. So what will happen? The direction of movement of electron towards OH bond takes place, and hence here the polarity of OH bond decreases because the electron density of oxygen atom is increased by the electron donating group of alkyl group. But in phenol, no such groups are present, and hence the acidity of phenol is not influenced. But in the case of nitrophenol, the oxygen atom of nitrogen, which is more electronegative, and hence the electron density of oxygen is reduced and it is pulled by the NO2 group. So here the electron density of oxygen decreased by NO2 group, and hence increases the polarity of OH bond. Therefore, the electron donating group at para position increases the acidic character of phenol. So this is here polarity increases. So in general, electron donating group that decreases the polarity of OH bond, and hence those are weaker acid than phenol. But the electron withdrawing group present in phenol that increases the acidic character of phenol. Therefore, electron withdrawing substituted groups that behaves strong acid than phenol. All alkyl groups are electron donating group. The electron donating group, you can observe the EDG are halogen, NH2, NH or NR2, alkoxy, alcohol. These are all electron donating groups. Electron withdrawing groups are NO2, CHO, CN, COOH, ketone. These are all electron withdrawing group. So the presence of electron withdrawing group that increases the acidity of phenol, the presence of electron donating group that decreases the acidity of phenol. Dihydric alcohol. An example of dihydric alcohol is ethylene glycol, the first member of dihydric alcohol. It is CH2OH, CH2OH. This dihydric alcohol contains two primary alcoholic group CH2OH, CH2OH, both of them are primary alcoholic group. Whatever the primary alcohol undergoes the chemical property, all those properties will be given by ethylene glycol. How ethylene glycol is prepared? Ethylene glycol is prepared from ethene. When ethene is oxidized in presence of Bayer's reagent. Bayer's reagent is cold dilute potassium permanganate, alkaline solution of potassium permanganate. It is a Bayer's reagent. We said dilute, so it has water, and the permanganate is an oxidizing agent, so it has to provide the nascent oxygen. So the water, you can write it as HOH, and you may find there are OH group and these two will make another OH group. So both OH group getting adds between the two carbon atom, doubly bonded carbon, so we are getting ethylene glycol. What are the properties of glycol? Already, as I said, it has two primary alcoholic group. Primary alcohol that will undergo reaction with the sodium metal where hydrogen is displaced. Also, it reacts with the thionyl chloride, phosphorus trichloride, phosphorus pentachloride. So, such reactions can also be observed in ethylene glycol. When it reacts with the metals, both of the hydrogen atom, this hydrogen and this hydrogen subsequently replaced by sodium metal. So, the final product of glycol will be disodium ethylene glycolate. Disodium ethylene glycolate. Similarly, that may also undergo halogenation reaction with the phosphorus trichloride or pentachloride. Even we can add thionyl chloride too. So, in this case also, we will get 1,2 dichloroethane. Then reaction with phosphorus triiodide. When ethylene glycol reacts with the phosphorus triiodide, it is converted into ethane. It is an important question. How will you convert glycol into ethane? When it is treated with the phosphorus triiodide, both the OH groups are substituted by the iodine atom. And the phosphorus will be left as, we know well, with the trihalide, the phosphorus will be left as H3PO3. And the presence of 2 iodine to the adjacent carbon atom of ethylene, what happen? They will find steric effect or occupational effect, since both iodide ions are much bulkier than those of either chloride or bromide or even fluoride. So because of such bulky group to the adjacent carbon atom, that makes the compound unstable. That's why it is put into the square bracket. Any structures inside the square bracket, that is referred as unstable. So subsequently the iodide getting removed as iodine molecule. Therefore we are getting ethane. Reaction with the nitric acid. Nitration also possible in ethylene glycol. This is possible only in presence of concentrated sulfuric acid. As ethylene glycol has 2 OH group, it requires 2 numbers of nitric acid. So it is split up and write HNO3, HNO3. Actually we have taken 2 molecules of nitric acid. So in this case, the hydrogen atom of is displaced with OH of nitric acid as water molecule, and hence the product will be CH2O NO2, CH2O NO2. This is called dinitroglycol. Then dehydration reaction. Dehydration reaction that can be carried out with glycol under different conditions. When glycol is heated alone at 773 Kelvin, there would be a loss of water molecule between the adjacent OH group. So we will get ethylene epoxide. The compound is said to be ethylene epoxide. At the same time, when it is treated with dilute sulfuric acid or anhydrous zinc chloride, it forms an unstable where a loss of water molecule takes place, minus H2O. This OH group from the adjacent carbon from the adjacent primary alcohol, that OH that is left as like that. So here the single bond between the carbon makes double bond and OH with the hydrogen removed as water. So we have CHOH and it undergoes rearrangement this way. So we are getting CH3 single bond CH double bond O, that is CHO. So acetaldehyde is formed. So ethylene glycol on heating converted to ethylene epoxide with anhydrous zinc chloride or dilute sulfuric acid, it forms acetaldehyde. Suppose ethylene glycol is treated with the concentrated sulfuric acid on distillation, it gives 1,4 dioxane, 1,4 dioxane. Here 2 molecules of ethylene glycol taken, a loss of water molecule takes place at both the end of the OH group. So we are getting CH2O, CH2, CH2O, CH2. This is known as 1,4 dioxane. Oxidation of glycol with periodic acid. Periodic acid is HiO4. Formula for periodic acid is HiO4. So 3 of the oxygen atom doubly bonded with the iodine and 1 more oxygen is present as OH. The presence of OH group that makes the compound as acidic. So in this case, the periodic acid, one of the oxygen that reacts with the OH group of ethylene glycol and it is left as minus H2O. So we are getting an adduct. From this adduct, we can find there is the subsequent movement of the bond among the molecule and hence we may get the 2 molecules of formaldehyde. This bond broken, so CH2O, this makes 1 formaldehyde and this bond make over here, so this molecule makes another formaldehyde. So we are getting 2 molecules of formaldehyde and the rest will be IO3, that is HIO3. We are getting iodic acid. So we are getting 2 molecules of formaldehyde with iodic acid. So periodic acid is reduced to iodic acid and ethylene glycol is oxidized to formaldehyde. Oxidation of ethylene glycol. The previous case we discussed about the oxidation of ethylene glycol with periodic acid where we got formaldehyde as the product. Here, when ethylene glycol is oxidized either by nitric acid or by potassium permanganate, alkaline potassium permanganate. If you take alkaline potassium permanganate, the final product will be oxalic acid. The final product will be oxalic acid. Ethylene glycol straight away oxidized to oxalic acid in presence of potassium permanganate under alkaline medium. But when you take the nitric acid, it may undergo the stepwise oxidation of glycol. And this glycol, it has both of them, the 2 primary alcoholic group. We know primary alcohol oxidizes to aldehyde and then to acid. So such a way, when you consider the reaction, you may find the progress of oxidation of ethylene glycol. See, let us see first of all this primary alcohol, it is oxidized to aldehyde. So here we are getting glycolic aldehyde. So the primary alcohol oxidized to aldehyde, this is called glycolic aldehyde. And upon further oxidation, aldehyde is oxidized to COOH because primary alcohol to aldehyde, aldehyde to carboxylic acid. This is called glycolic acid. And the first primary alcohol is converted into carboxylic acid. The next stage, the second primary alcoholic group undergoes oxidation. So this primary alcohol that is converted into aldehyde, this is called glyoxalic acid. It is called glyoxalic acid. And further oxidation, this aldehyde is oxidized to carboxylic acid. So we are getting oxalic acid. So in the first case, the both primary alcohol subsequently oxidized to their respective carboxylic acid. So we got the product of glycolic aldehyde, glycolic acid, glyoxalic acid and oxalic acid. Instead of this way, here the first primary alcohol oxidized to aldehyde. In the next stage, this primary alcohol, when it is oxidized, we are getting both of them are converted into aldehyde. This is called glyoxal. And upon further oxidation, this aldehyde is oxidized to COOH, and on further oxidation, glyoxalic acid is oxidized to oxalic acid. So the learning process is very important. We have to consider only one of the primary alcohol at a time. When you change the first primary alcohol up to acid, then you have to take the secondary primary alcohol up to acid. Or you have to consider both the primary alcohol to aldehyde, and then it can proceed the subsequent oxidation to carboxylic acid. So these products will be obtained depends on the nature of oxidizing agents we have selected for oxidation of glycol. Followed by dihydric alcohol. Let us discuss about trihydric alcohol. The first member of trihydric alcohol is glycerol, or you can say glycerin. This is CH2OH, CHOH, CH2OH. In this we may find the compound, it has two primary alcoholic group and one secondary alcoholic group. It is prepared by the saponification reaction. What do you mean by saponification? Saponification is nothing but the preparation of soaps from palmitic acid or the oleic acid or the stearic acid. Palmitic acid, stearic acid, oleic acid, these are and all present in vegetable oil in the form of glycerides. So here we have taken one of the glycerides, those are in ester form, and here the R group is taken as CH3 CH214, that means the name is palmitate. So when such glycerides undergoing hydrolysis with alkali, so when palmitate is hydrolyzed by sodium hydroxide, the formation of soaps obtained such a way. So the bond it breaks here and that makes RCOONA or COONA. So 3 times of RCOONA, that is the sodium salt of higher fatty acids, are called soaps. So we are getting soap. This is usually the edible oil contains too many number of carbon atom, like having 15 to 17. So such acids are said to be fatty acids, and hence the soap formed is also called sodium salt of higher fatty acids. So upon the removal of the sodium salt of carboxylic acid, you may find the 3 hydrogen atom to the CH2O group. We are getting glycerol. So glycerol is the major byproduct of saponification reaction. Reactions of glycerol. Glycerol has 2 primary alcoholic group and 1 secondary alcoholic group. Just like glycol, this also undergoes nitration, where there is a formation of 3 molecules of water, H2O. So minus 3 H2O, we are getting CH2ONO2, CHONO2, CH2ONO2. This is called trinitroglycerin, an explosive substance. And upon the dehydration by heating with potassium hydrogen sulfate, it forms acrolein. This is test for trihydric alcohol. This can be taken as test for glycerol. So when it undergoes the loss of water molecule from the adjacent OH group, we are getting an unsaturated aldehyde called acrolein, and that has offensive odor. So the loss of water molecule takes place between the primary carbon and the secondary carbon of hydrogen OH, and from the primary carbon of next one to secondary oxygen, that is loss of water molecule. So because of the subsequent removal of water molecule, carbon-carbon double bond develops and carbon-oxygen double bond develops. So we are getting acrolein. Oxidation of glycerol. When glycerol is oxidized, based on the type of oxidizing agents we have chosen, we will get the variety of products from glycerol. So as it has two primary alcohol and one secondary alcohol, the primary alcoholic group will be oxidized to carboxylic acid through the formation of aldehyde. Secondary alcoholic group that can be oxidized to only ketone. So by keeping this idea, you can have the oxidation with the dilute nitric acid. First of all, one of the primary alcohol oxidized to carboxylic acid and followed by the secondary primary alcohol is also oxidized to carboxylic acid. So with the dilute nitric acid, the glycerol that undergoes oxidation only to the primary alcoholic group, and hence you are getting glyceric acid and tartronic acid. Suppose concentrated nitric acid is taken, only either out of these two CH2OH, only one of the primary alcohol oxidized, and hence you will get mainly glyceric acid, tartronic acid won't be produced. Or with the bismuth nitrate, both of all the primary alcohol and secondary alcohol oxidizes. Primary alcohol, it oxidizes to carboxylic acid. This primary also carboxylic acid, but secondary alcohol to ketone. So we are getting mesoxalic acid. But with bromine water or sodium hypobromite or Fenton's reagent, this FeSO4H2O2 is said to be Fenton's reagent. So when this either of the one is used, you may find either primary alcohol or the secondary alcohol will be oxidized. If primary alcohol oxidized, aldehyde. If secondary alcohol oxidized, ketone. So it forms the mixture, and the mixture of this one is known as glycerose. Here the name of the compound glycerol to glyceraldehyde. This is dihydroxy 3-carbon ketone. So it is dihydroxyacetone. With periodic acid or lead tetraacetate, this glycerol decomposes into formic acid and formaldehyde. But with the strong oxidizing agent of acidified potassium permanganate, glycerol oxidizes to oxalic acid. So these are the different products obtained from glycerol. Depends on the nature of oxidizing agent. When you learn, you have to identify which of the group is oxidized to which form, whether aldehyde or ketone or acid. By knowing this, you can identify and remember the reactions with respective oxidizing agents. Methods of distinction between primary, secondary and tertiary alcohol. Already we discussed about Lucas test, concentrated hydrochloric acid and anhydrous zinc chloride. Depends on the turbidity formation, we can classify whether it is primary, secondary or tertiary. The other one is Victor-Meyer test. This Victor-Meyer test, it involves 4 steps. The first step is conversion of alcohol into iodoalkane and iodoalkane to nitroalkane, followed by treatment with the nitrous acid. It may give the substituted product, where depends on the formation of colors, we can identify whether the given alcohol is primary or secondary or tertiary. Suppose the primary alcohol, when it reacts with phosphorus and iodine, it forms iodoethane. This is followed by treatment with silver nitrite. It is silver nitrite. So here the AgI will be removed. So in this case the OH is replaced by I. Here AgI is removed. So minus AgI. And we are getting nitroethane. This nitroethane on treatment with the nitrous acid, N double bond OHO. This is nitrous acid, HNO2. Here, this 2 hydrogen that combines with this oxygen, so there is a loss of water molecule where you may find CH3, C double bond NOH with NO2, CH3, C double bond NOH with NO2, and followed by treatment with potassium hydroxide, it forms the salt of the compound CH3, C double bond NOKNO2. This is in red color. So the salt of nitrolic acid, the previous compound formed is nitrolic acid. This nitrolic acid on treatment with potassium hydroxide, it gives red color. Let us take the secondary alcohol. The first one is primary alcohol. This is secondary alcohol. When it is also treated with the phosphorus iodine, the OH is substituted by iodine. So we are getting 2-iodopropane. This is followed by treatment with the silver nitrite. This AgI is removed. So minus AgI, we are getting 2-nitropropane. So this is 2-nitropropane, followed by treatment with nitrous acid. Here the hydrogen atom of CH that combines with OH of nitrous acid, so minus H2O. Here you are getting nitropropane, where the formation of the product is blue color. This is 1, 2, 3, 2-nitro-2-nitrosopropane, whose color is blue color. With the tertiary alcohol, once again it is treated with phosphorus and iodine, where we are getting 2-methyl-2-iodopropane, followed by treatment with the silver nitrite. So minus AgI left. So we are getting the tertiary nitro compound. This compound is colorless and it does not react with the nitrous acid because this functional carbon has no hydrogen. So you may find the primary to tertiary alcohol. When the primary carbon has H2, you are getting the loss of water molecule forming double bond NOH. But in the secondary alcohol, the functional carbon has only one hydrogen, so that combines with the OH of nitrous acid, so you are getting nitro derivative. But in this tertiary alcohol, the functional carbon has no hydrogen, so it can proceed only substitution reaction with the phosphorus iodide and silver nitrite. But the further reaction with the nitrous acid and even with the potassium hydroxide does not take place, and it becomes colorless. And this one, the secondary one, after the formation of nitrous or nitro derivative, there is no reaction with the potassium hydroxide, since this NO group, it has no replaceable proton. That's why it does not react with potassium hydroxide. So Victor Meyer's test is an important method by which the 3 different types of alcohols can be distinguished depends upon the formation of colors. Chemical test to differentiate alcohol from phenol. So how phenol can be differentiated? If any compound is given to you, you have to identify whether the given compound is aliphatic or aromatic. So here we have alcohol and phenol. If the compound given to you alcohol or phenol, we have to identify by using simple chemical test to identify whether the given compound is alcohol family or phenol family. Identify this test, we can have a coupling reaction for phenol, or the treatment with the neutral ferric chloride, or with the sodium hydroxide test. Phenol that will undergo coupling reaction to form red-orange dye with the benzene diazonium chloride. And phenol that gives purple coloration or violet coloration with neutral ferric chloride. This neutral ferric chloride, when it is treated with the phenol, it forms iron triphenoxide. So plus 3HCl, the formation of this compound that gives rise to purple color. But alcohol do not react with ferric chloride. Sodium hydroxide test, we know well, phenol reacts with bases to form sodium phenoxide and water, but alcohol do not react with sodium hydroxide. Besides sodium hydroxide test, you can take the coupling reaction and the neutral ferric chloride reaction is the best method for the distinction of alcohol from phenol. And when the questions asked for differentiate from test for chemical, give a chemical test to differentiate alcohol from phenol, definitely you have to write the chemical equation. Not supposed to write only the statement. The statement has to agree with the chemical equation. So you have to write the chemical reactions also for the chemical test to differentiate any two compounds. Recap of today's session. Recap of today's session. Today we discussed about the acidic behavior of phenols and alcohols, and we also discussed about the influence of electron donating group and electron withdrawing group to the acidic behavior of phenol. And along with that, we discussed about the dihydric alcohol and trihydric alcohol, their preparation along with their properties. Victor Mayer's test, by which the three different types of alcohol, how they are identified depends on the formation of color, that too discussed. And upon which, and also we discussed about the chemical test used to distinguish alcohols and phenols. Okay students, let us close our today's session and we will continue the next session from the same chapter. Until then, bye bye.